It's time for our webinar to begin this afternoon or this morning if you're on the West Coast. Would like to welcome everyone. The webinar this afternoon is going to be presented by Dr. Jean Bartholomew and myself. I'm Don Zink. And we want to talk to you a little bit about sampling and testing, primarily pathogen sampling and testing. And let's just go right to slide 3 with our agenda. And in trying to think about the scope of this, there's a lot of different things you can test for: chemical hazards, microbial pathogens, indicator organisms. We think one of the things that's most important to get right is pathogen testing. And so in the time we have available, we're going to put our emphasis on pathogen testing and sampling plans. And it's really not, the presentation is not meant to be a treatise on the statistics of sampling, but yet we acknowledge that you have to understand some underlying statistical concepts in order to really appreciate what kind of sampling plan that you need. Also, we're really not going to talk about test methods. And in truth, most of the common test methods for pathogens out there in use right now are very good. Most of them are probably within 5% of each other in their performance. And while it's true that some may be better than others, I think that by far the biggest problem we face in the industry is having ineffective sampling plans. And if you have a poor sampling plan and a great test method, you're still going to get a poor result. And it's really very important to get the sampling plan right. If you don't have a good chance of finding the target pathogen in your sample, then it really doesn't matter how sensitive your test method is. And another area that's very important to address is what's going to happen when you get a positive result. Very early in my career in the food industry, I thought, well, we'll just test for such and such. And a more senior person in those years explained to me, oh, no, don't you dare just run out and test for something before you've thought about how you're going to react to a positive result and what the implications of that positive result might be. I don't want to discourage anybody from doing appropriate testing, but trust me, when you're faced with a positive result, that is not the time that you want to sit down and try and figure out what the implications are. Next slide, please. We're going to have a poll question here, and we'll talk about it towards the end of the presentation, but we'd like for you to just take 1 or 2 minutes here to respond to this poll. And it might be interesting just to see what the results are when we get to the end of the poll, and perhaps ask people if the presentation would have made them answer differently after the presentation. So I'll give you just a few minutes to answer the poll. Okay, let's move on to the next slide. So the one of the key concepts and one of the areas where companies are criticized by regulatory agencies is when what you're doing isn't really reflected in your food safety plan. So there really needs to be a connection between your food safety plan, the hazard analysis, and what you're doing with testing. Very often, you will identify a pathogen as a pathogen of concern and one that requires preventive control. At this we may be talking about an ingredient or a finished product, or we may be talking about the environment. But if you've identified pathogen control in your food safety plan as something that's requiring a preventive control in an FDA regulated plan or in a HACCP plan with the USDA, then you really should have that in your testing, and that testing is ordinarily going to be the verification of the effectiveness of your control. Testing itself is rarely accepted as a preventive control, but it's always accepted as verification. Occasionally, testing, particularly in the case of, say, finished produce or any product that does not receive a kill step, testing can be a risk reduction step. For example, if you can identify a ready-to-eat ingredient and detect that it's contaminated with a pathogen, you can keep it out of the food product distribution stream and thereby reduce the risk of public health and reduce the risk of liability to your company. I'd also like to say a word about indicator organisms. Indicator organisms really often aren't. When it comes to pathogens, I'm aware of only one truly honest indicator organism, and that would be using Listeria species as an indicator for the possible presence of Listeria monocytogenes. Every other indicator organism that you can think of, whether it be coliforms, fecal coliforms, generic E. coli, or even Enterobacteriaceae, is a very much flawed indicator organism. Others in my profession have gone on record as saying that we really need to quit doing tests like coliform, fecal coliform, E. coli, and Enterobacteriaceae testing. These things really don't have the value, and although my company is in the testing business and we're happy to do these tests for you, we would rather you didn't. We would rather you put your resources and your efforts onto proper verification and validation testing and pathogen testing where it needs to be done. These organisms simply do not have any predictive value as to whether a pathogen can be present in a lot. They often cause a lot more trouble and aggravation than they're worth. Now, that's not to say that you can't use some testing for organisms, microorganisms, to indicate when perhaps you may have sanitation problems. And certainly you could do something like Enterobacteriaceae or aerobic plate count testing of equipment surfaces to demonstrate effective sanitation. But most of what you want to do with indicator organism testing can be done with the aerobic plate count. And the aerobic plate count, of course, is going to capture a much wider variety of microorganisms than these other tests are going to do. And it can be an indicator of sanitation, but it is, again, not an indicator that there may be pathogens present. And finally, one of the things that you must think about in making a decision about testing is the law of unintended consequences. There are several ways you can get into trouble doing pathogen testing if you don't give some thought to this. For example, let's say you're testing an ingredient that is supplied to you from one of your trusted suppliers. You're testing this ingredient for the presence of a pathogen like Salmonella. And let's suppose you get a lot of that ingredient in and you test it and you find Salmonella. Even though your supplier may have tested it and gotten a negative result, we know that it's possible that you would get a positive result. Well, now you've created quite a situation for your supplier. particularly if they have already sold this lot to a number of other companies. They're now in the position where if this is an FDA regulated food, you're going to have to file a reportable registry report, and they're probably looking at multiple recalls related to it. I suppose on the upside, it's good to detect a pathogen contaminated ingredient, but on the downside, you will not get a gold star from your supplier on that day. And your supplier may very well tell you, go find yourself a new supplier. So that's something you need to think about. Certainly something you need to work out with your supplier in advance. Also, if you have a positive result on something like a food contact surface or an ingredient that's added after a kill step or on a finished product, you have to think about how this might impact other lots, perhaps lots you've produced previously and already released because they had a negative result. We see this occasionally when one of our clients gets a positive result on a lot, and they end up, the good news is that lot was on hold, but the bad news is they end up implicating other lots that they've already produced and released. And of course, at that point, you're looking at a recall. So there's a lot to think about prior to doing some testing. Next slide, please. So every regulatory body you can think of, and we could have made this slide list even longer, but FDA, USDA, WHO, FAO through Codex Alimentarius, everybody requires and recommends and endorses microbiological testing for pathogens for the purpose of verification. It's just not something that's debated anymore. We all believe that we have good and robust control programs, but it's necessary to do a certain amount of verification testing to demonstrate to ourselves in an ongoing way that our control programs are actually working. When you find a pathogen in a finished product, it almost always means that one of your control programs or more simply aren't working. Next slide, please. These are some examples or situations where verification testing could be important. First, I'll give you an example where verification testing isn't very common or important. If you're a manufacturer of low-acid canned foods, we don't commonly pull samples of those cans out and do tests for pathogens on them. Nobody in the canned food industry pulls a few cans off the line and tests them for something like Clostridium botulinum. That's a case where we have such robust thermal processes and ability to control those processes in that industry that what we do for verification testing there might be nothing more than a small set-aside program to verify commercial sterility. So certainly not every food product has to undergo some finished product testing or sampling. And indeed, in the canned food industry, the failure rate where we have a food safety problem is on the order of about 1 in 10 billion. And wouldn't do much good to try and devise a sampling plan for that anyway. We'd end up testing all the cans we produce. So we do testing usually in other processed foods or foods that don't receive a process. In the case of fresh produce products, something like bagged leafy greens, these things really don't get a significant lethality treatment. They may well undergo treatments that reduce risk, but we're not talking about anything like a 5 or a 7 log kill for most of these processes. And what they go through is really risk reduction. And in that case, doing microbiological testing is really seen as of the finished product is seen as a means of verifying all that you've done under good agricultural practices and sanitation in production, et cetera. And it can also be a risk reduction strategy. Testing ingredients that are intended for raw products can be an ongoing way to verify that your supplier is doing their job. In many cases with FDA regulated foods, we're buying an ingredient from a supplier and we're putting it into our food without a further kill step. And our food safety plan may treat that as a supply chain preventive control, where we're relying on a pasteurization process by our supplier. And in that case, doing some testing or working with the supplier on testing is how we verify the ongoing control. And products that receive a lethality treatment, but that might be vulnerable to contamination from the environment, those are also products that we can use finished product testing to verify both that our lethality treatment is being properly applied and that our environmental pathogen controls are working as we've intended. Next slide, please. So how frequently and when is testing conducted? I think there's two things you really should think about for these questions. And one of them is, how much risk can you tolerate? And another is you should always remember the risk equation, that risk is equal to severity and probability. If you're talking about a very serious pathogen like salmonella, it's quite severe if it were to be ingested by one of your customers. You also have to think about probability. In situations where the risk is very severe or where the pathogen is very severe and the probability of finding it is very high, then you could hardly be justified in testing every third lot. When your risk equation is high, that's when you need to have fairly frequent testing. And the frequency of testing is a factor of how frequently do you need to sample and test in order to detect a problem. And also, how much risk can you tolerate? If you really cannot afford to have contamination slip through on one of your production lots because the risk is severe or particularly probable, then that's going to dictate a more intense testing program. And, for example, fresh produce, studies have been done that show you can significantly reduce risk if you test in the field before harvest, as well as in process and finished product. You can achieve better than a 10-fold reduction in the risk of shipping a contaminated product if you follow a protocol like that. And one of the reasons, of course, is contamination can occur in the field. If we can keep that contamination out of the plant, we reduce the risk that it will be spread from in the case of leafy greens, from leaf to leaf or bin to bin by our washing and handling protocols. And contamination can occur during the washing and packaging procedures. And if we can sort that product out in process, then we increase our chances of having negative results when we do finished product testing. So you've got to think about your risk. You've got to think about the points of contamination and design your sampling plan accordingly. let's have the next slide, please. So a lot of you are familiar with the familiar normal distribution chart on the left. And anyone who's ever taken a course in statistical process control will understand that probably you've been subjected to many examples of manufactured products and sampling plans and defect rates and what sort of plan you need for a particular defect rate. And in fact, there are a number of food products out there where if they become contaminated, they could very well have a contaminant that indeed follows this normal distribution, this so-called bell curve. A product that might follow this bell curve is a product that gets extremely well mixed. It might be a liquid product, for example. If you pump a liquid product into a rail car or a truck tanker, by the time that load gets there, it's going to be pretty well mixed, and it's anything that's in there is going to probably be uniformly distributed, and the statistics that one might use for binomial probability would work quite well for you. But that's not the case with a lot of food products. A lot of food products are solid or semi-solid. And in the food industry, we often produce things in what's called a continuous batch, where we make a batch of a product and we send that then down the production line. And then we make another batch and send it down the production line. And while we do everything we can to make these all the same, in truth, there can be microbiological heterogeneity there, and what's in one might not be in another. Also, imagine a production line where you may have a pathogen contaminating food contact equipment on that line, and every once in a while during the day, a bit of that pathogen gets sloughed off by the movement of product over it and creates a bolus of contamination in your production stream. You might see something like this in a powdered spray-dried milk operation. You might see something similar, although maybe with a different cause. If you're making ground beef, you might get a highly contaminated piece of trim that goes into the system and contaminates a volume of product that perhaps may not be more than just a couple of minutes of runtime on the production line. So it's more common in the food industry, from what I have seen, that contamination is both non-random, although we may not always know the cause, and it's not uniform. I've certainly seen uniform contamination, but most of what I see is contamination that occurs infrequently, intermittently, and that when you look at the entire lot, only a very small percentage of this product is actually contaminated. Maybe, and I think most commonly, less than 1%. And that becomes challenging from the standpoint of statistical sampling plans. You've all heard of this proverbial needle in the haystack that we're looking for when we're trying to find a pathogen that could be in a very small quantity out of, say, a 20, 30, 40,000 pound lot of product. So what to say? If there's a lot written about sampling plans when you have a normal distribution, not so much when you don't have a normal distribution. In fact, when you don't have a normal distribution, it is impossible for you to predict exactly what the performance of your sampling plan is going to be. But I can tell you that generally, a sampling plan that favors a larger number of samples per lot is going to give you a much better result than a sampling plan that simply favors fewer samples or larger quantities of product. And I want to go through, well, first let me show you how sampling plans might perform if you're following this kind of normal distribution. Next slide, please. This is the very, to those of you who've ever read any of the very good ICMSF books on microorganisms in foods, this is a often reproduced table that shows you the effect of increasing the number of sample units from a lot on your probability of detecting a lot that is truly contaminated. And this again assumes that the microorganisms are normally distributed, following that bell curve distribution in your lot. So if I look at the top row here, if you have a lot is you may not know this, but let's say that this lot you have that you're questioning is 98% of the units in it are acceptable, but 2% are contaminated with a pathogen. So what does this table tell you? Let's say you're one of these companies that likes the idea of pulling 3 samples per lot, beginning, middle, and end of the lot. That's very popular. It's compelling. It has symmetry to it, if you will. So you pull 3 samples. What are the chances that your sampling plan is going to end up with the pathogen in one of those samples and you'll detect it? Well, the answer is not so good. The table is telling you there's a 94% chance that your test results will come back negative and this truly defective lot will be released by you. But if you go all the way over to the right-hand side and you decide you're going to pull 100 samples from this lot, you're going to pull a sample however frequently during the production run, that at the end of the run, you'll have a total of 100 samples, and you combine these and test them. And what is your probability then of finding this defective lot? Well, it turns out it's quite good. At this time, there's only a 13% chance that you will end up releasing, that you'll get all 100 samples negative and you'll end up releasing that lot. To me, frankly, 13% sounds a little scary. I'd like to do better than that if I could, but then again, 100 samples, that's a lot of samples. But there's a huge difference between a 94% chance of accepting a defective lot and a 13% chance of accepting a defective lot. Now, if your lot is really defective, 60, 70, 80% defective, well, then it doesn't take very many samples to detect a lot like that. But remember, with pathogens in food, most of the time we're looking for that needle in a haystack. And there is one very good example, case study, that I want to walk you through in the next 3 slides that kind of shows you the real world. So if we could have the next slide. So this slide is from a paper published in 2011 by Jonenberger and others, working out of University of Nijmegen in the Netherlands. And they had the good fortune to be located in proximity to a powdered infant formula plant. And this powdered infant formula plant, one of the pathogens of concern in powdered infant formula is Chronobacter sakazaki. You don't need to know a lot about the organism except that it's really bad news in powdered infant formula. And so every manufacturer of powdered infant formula tests all of their finished product lots for Chronobacter sakazaki. And in the course of producing this lot, the manufacturer tested their production lot, and it was positive. And ordinarily, a positive product like this in an infant formula plant would be destroyed. It would be shipped off to animal feed or a landfill. But the university somehow got wind of it and talked them into setting that lot aside and working with them to study that lot. And they had the advantage of having all these containers of powdered infant formula with the time stamp on it. So they knew the exact time the product was filled. And it was filled over a period of 24 hours. I don't really know how much product was involved, somewhere between 20 and 40,000 pounds. And probably it was divided into 1 or 2 pound bags or containers. So they went through and sampled virtually every minute. They took thousands of samples, and they did both presence absence testing, and they did quantitative testing. And of course, they were able to record the time stamp of when the product was filled. And so what this chart shows you is this is a testing they did where they were testing 1 gram for the presence of a pathogen and enumerating it. Their limit of detection in this particular case was 95% confidence interval was 3.3 colony forming units per gram. That's the dotted line here. And so what they found is that the most significant contamination, the contamination that had the largest number of organisms, occurred at 14 hours approximately into filling the product. So imagine in this whole 24-hour period, the bulk of the contamination occurred only once and only for a few minutes, right about in the middle of the filling. Well, if you had one of these sampling plans where you're only looking at product about every 30 minutes, there's a pretty good chance you might have missed it. At any rate, let's take a look at this a different way in the next slide. So this slide excerpts some of their data and shows it to you in numerical form. If you go over and look at the slide, you'll see between 13 hours and 58 minutes into filling and 14 hours and 7 minutes is when all the contamination occurred. And in fact, if you look at this, it all pretty much occurred between 13 hours and 58 minutes and 14 hours and 4 minutes. That's a period of time of only 6 minutes out of 24 hours. And at 1400 hours, one of the cans had 560 colony forming units per gram of product. So what's nice about this is now we know the concentration and distribution of contaminants in the lot. This is something we never know on foods that we're ordinarily producing. We don't sit down and do 2,000 samples on a lot of food. So we don't do it quantitatively. So this was a unique opportunity. Now that we know the distribution of contamination and the numbers, we can calculate how various sampling plans would have performed. So let's look at the next slide. So this shows you, using this real world example, this shows you what would happen. And what I'm going to do is walk you through a situation here where we look at keeping the total amount of product that we test the same, but taking in different numbers of samples. For example, we could take a single 300 gram sample. What are the chances that that single 300 gram sample is going to detect contamination in this lot? Well, pretty poor. In truth, there was some very low level of contamination below the limits of detection that were present in the lot. But when you factor in all of that, this sampling plan only has a 37% chance, 37.83 to be exact, chance of detecting contamination in that lot. Well, what if we go to a beginning, middle, and end strategy, and this time we collect 3 100 gram samples? Great, our odds improve. Now we've got a 61% chance of finding that positive result in this lot. That's still not very good. I mean, we're talking infant formula here, and we're talking about a pathogen that is highly likely to kill a young infant. This pathogen causes brain abscesses and meningitis. It's bad. I'd like to do better. Well, if you use a sampling plan where you collect 10 samples of 30 grams each, now you're up to a little better than 89% chance of detecting a positive. But still, what about taking 30 samples of 10 grams each, still 300 grams? Now you're up to 96.8%. And incidentally, this is the regulatory standard for infant formula in most of the world. If you look at Codex and a lot of countries' regulations, they require that you test 300 grams as 30 samples of 10 grams each. That's pretty good, 96%. And that, I think that explains why this company detected this positive lot. You can do better. You can take 100 samples of 3 grams each or 300 samples of 1 gram each, and you're going to be better than 99% chance of detecting contamination. But look here, if I triple the amount of product I test, still using 30 samples, the improvement I see goes from 96.8% chance of detecting it to 99.8%. And if I go all the way up even more to 1,800 grams, well, then I get to about 100%. So what this tells you is if you want to get the most bang for your buck, increase the number of samples, not the total weight of the samples in grams. So that's my part of the take-home lesson. I'm going to turn it over to Gene now.
Okay, thank you, Don. So let's go back to the ICMSF case 15, which you probably don't remember, but that's a common one that's used in the food industry where the number of samples pulled from a lot is 60. And the C equals 0 just means that we're doing presence, absence, and any presence of a pathogen would result in a failed test. So this is a common sampling plan. And let's assume in those small cases where the pathogen is uniformly distributed throughout the product, if we take 60 samples and each sample weighs 10 grams when we analyze it, and somehow we knew ahead of time that in that large lot, 5% of every 10 gram aliquot actually had a pathogen in it. To reiterate what Don just said, even though it seems like we're taking a lot of samples, 60, there's still a 5% chance that we do not detect pathogens in that lot, and then we release that lot as acceptable. So that shows that even large sample numbers have some risk in terms of releasing contaminated lots. Well, Don was talking about sample weight as well. So if you keep everything else the same, but you do actually increase your sample weight, let's say you go from 10 grams to 25 grams, I hope that makes sense to you that the likelihood of detecting a pathogen goes up if you keep the sample number the same, n equals 60 or n equals whatever number you want to pick, but your actually sample size goes up. The same is true, and in fact, a lot of people now are sampling product samples at 75 or in some cases 325 grams. So it does help under most circumstances to increase sample size. But I think the sample number is the more important number to keep in mind. So I'm going to reiterate some of the things that Don said because we want to drive home the importance of this. Defects are typically not uniformly distributed throughout our lots. So if a defect is not continuous, and this could happen any number of reasons, such as let's say we have a GMP violation, an employee does something on the line and it perhaps only happens once during an 8-hour shift, or you had a slight power fluctuation and the temperature dropped for a very short period of time in your cook oven, you may not know that those things happened, and you would see a potential discontinuous process control and therefore a resultant contaminant. So if you pulled samples like Don mentioned at the beginning, the middle, and end of a run, even if you pulled 10 or 20 at each one of those time intervals, you very well could miss a defect in that lot because it happened during one of the times when you were not pulling samples. So the time that you pull samples is very important if you're trying to catch these non-uniform errors in your process. Likewise, if you have an extremely large lot and you sample at uniform intervals, so you think about the Chronobacter example, if I was pulling samples every 15 or 20 minutes and did it the entire production lot, depending on how those 15 or 20-minute intervals were timed, you may actually have entirely missed that big spike that we saw in the example. So again, keep in mind that timing of sample collection is important, and it's based on both the non-uniform occurrence of these contaminants, and also in some cases, if you have an extremely large lot, it's very difficult to really sample that lot unless you're taking a lot of samples. So let's go to the next slide, please. So we're talking about lot size here. To some extent, defining a lot size is a business decision. So to some extent, how risk averse is your business? It's related to some extent to the volume of product per hour or per line. So if you have a very large production volume or a very fast line speed, you may want to have smaller lot sizes. So you can get a better handle on when to take an appropriate sample. You also have to think about what is the cost of my product if in fact I am detecting a pathogen and I have an extremely large lot size and I pull a sample. Let's say that spike we saw with the Chronobacter, what if that happened in the first 10 minutes of production of material and we ran for 24 hours? We were going to throw out a lot of product based on a very short interval when we perhaps lost control and introduced that pathogen. So that's going to cost the company a lot of money. You also have to think about, what about the value of product if there is a recall, either because an outside testing organization like perhaps FDA or USDA pulls product off the shelf and tests it, or what if there's an outbreak that's linked to your product? So again, if either of those happen, obviously the cost to you as a producer goes up based on both the volume and value of product. So you need to keep that in mind when you're weighing the cost of the sampling program versus the cost and the risk that you're willing to take. Let's go to the next slide. Okay, pathogens. What pathogens should we be testing for either ingredients or finished product testing? So you probably already know that pathogens are not all the same. We have what some people call frank pathogens, or what I would call kind of a true pathogen. This is an organism like Salmonella or like E. coli 0157H7 that typically causes illness when consumed at a fairly low dose level. And even in healthy adults, if you consume this pathogen, it's likely to lead to illness. So these things are almost always pathogenic to humans when consumed. Those are slightly different from what we call opportunistic pathogens. These typically require either high levels or high dosages to cause illness in humans, or in some cases, they require that the human have some age group where they're immunocompromised or they're on cancer treatment, or for some reason their immune system is depressed. And so these are not normally pathogens when at low levels and consumed by healthy people, but they can certainly become pathogenic under the right circumstances. So that those two groups you have to think about when you're deciding what pathogens to test for. As Don mentioned, you also have to think about what are your products that you're producing and what does your hazard analysis in your food safety plan reveal about likely pathogens in those products. So you really need to target or focus on the kind of product you're producing and the hazard analysis that tells you these are typical pathogens that are associated with my product. And there's certainly a lot of information in the literature to guide you down the right path there. It turns out from a factual basis, even though we're making this sound like there's a lot of fine tuning that can be done here in choosing pathogens, that if you really look at what's being done in the food industry from a general perspective, typically there are three pathogens that are, or at least three families of pathogens that are normally tested in, certainly in finished product testing. So Salmonella, which we've mentioned several times, EHEC or enterohemerod, let's just call it E. coli 015787 and its relatives, and also Listeria monocytogenes. Most of you have heard of Listeria monocytogenes. So if you look at food product testing, 99% of current products are tested for one or all of these organisms. So that should help you decide. If you consider all of those factors, it should be hopefully fairly straightforward for you to decide what pathogen to test for. If we go to the next slide. So here's an example of a slide. So we're looking at FSIS, which is the inspection service in the Department of Agriculture for meat and poultry products. So if you look at the recalls of beef products for our old friend E. coli 015787, there came a peak in about the year 2002. There were a significant number of recall events in the United States. About that time, USDA instituted some higher level expectations on producers, particularly of ground or non-intact beef. They also introduced some new test methods, and they expected producers to use those test methods as part of a verification process for the control programs they had in place to control E. coli on beef. So you can see, if you're looking at the number of recalls from 2002 down to 2003, 4, and 5, there was a significant drop in the number of recalls of beef products, primarily because of this enhanced regulatory perspective on 015787 and the introduction of a relatively more robust testing program to find this pathogen and verify the control programs. Okay, let's go to the next slide. So here's what you guys, let's see what our poll answers are, just to remind you. So 65% of you said that you test all of your finished product for pathogens before release. Okay, that's a pretty high number, and that's, I suppose that depends. I know some industries test at a much higher level than other industries. If you look at question number 2, so the number of samples that you're pulling, it looks like if we Can you scroll that? No, I can scroll it here. So there are very few of you, 20% are testing at 60, which is the usual case 15, where we have n equals 60 and c equals 0 for the kind of the internationally accepted sampling plan. So only 20% of you are testing at 60 or more. Quite a few of you are testing at less than or equal to 10. I hope we have convinced you by now that testing, if your sample size is less than or equal to 10, you have a fairly low chance of picking up an actual contaminant in a lot, and therefore you have a high chance of accepting potentially what is a contaminated lot. So let's close that one. So let's go to the next slide, please. All right. So what are we going to do after we've done our product testing? Well, first of all, as Don mentioned, before you even put a sampling plan into place, please think about, what am I going to do if I have a positive result where I detect a pathogen in a lot of product? You really need to think this through clearly before you ever start a sampling plan. If you already had a sampling plan in place, I urge you to go back and really look at your sampling plan and make sure that you have everything in place that needs to be. One of the things that we haven't talked about, but is extremely important when you do pathogen testing, particularly for finished product, is you need to make sure that product is on hold until you get results back from the testing facility. So if you have product that you send out samples for pathogen testing and you go ahead and release that product, and the product comes back as being positive for a pathogen, you quite likely are in a recall situation. And believe me, the regulatory agencies have struggled with producers that have done this and for a long time, and they will come down pretty hard on you. So please make sure, if you're doing pathogen testing, that you make sure that product is on hold and you have some kind of a hard release program where it cannot get out of your facility until you are sure of the results. Another thing that you need to do, if you have a product positive on a finished product test, is you need to think seriously about, why did my process, which was instituted to control this hazard, why apparently did it fail? If we had an aggressive and successful control program in place, then we would not expect to see pathogens in finished product. That is the whole point of our control program. So we obviously had some kind of failure in our control program, and we need to go back and do some kind of a root cause analysis and figure out exactly what happened. How did we end up with a pathogen on product when the control programs were supposedly designed to eliminate that hazard? You need to make sure you take corrective action. You need to make sure that it is effective and that you verify that your corrective actions actually fix whatever shortcoming your control program had. And furthermore, you need to think about, if I had a failure in my process and I detected it on this particular lot, am I convinced that the lots I produced before this lot and perhaps after this lot were also subject to the same process failure? So you seriously need to think about, what am I doing with product from other lots other than the one that tested positive? So now you have product that has tested positive for a pathogen. What are you going to do with that? In many cases, a producer with a pathogen in a product is going to end up sending it to a landfill. It's just not worth trying to salvage that product. If you're doing that, which I recommend in most cases, your first loss is your best loss. Make sure that you actually track and document that this product was disposed of properly and didn't for some reason end up in the commercial market stream. If you think that you can divert this product to some other product that goes through a subsequent lethality step, then make sure you have the proper process controls in place to ensure that that happens. Likewise, if it's a raw product like ground beef that perhaps you detected O157H7 in, and you're going to divert that to a further processing converter who is going to heat that product to a lethality level before releasing, again, you need to make sure that that person has a written agreement with you that they will handle that product in the appropriate manner. You certainly don't want these products to come back and haunt you after you've figured out that you have a processing issue. So one of the things that I get asked once in a while is, if I'm producing product for a customer, let's say every week I produce a lot for a particular customer and one of the lots tests positive, do I have to notify that customer? Well, this is one of those gray areas, I suppose. Many customers would expect you to do that, but frankly, if you do not have it written into a contract, I'm not sure that I would volunteer that information unless you truly believe that you have not isolated the true cause of the failure to control a hazard. In that case, you may want to notify the customer that you're having production issues and that you're going to have to temporarily stop shipment to that customer. I think they will be glad that you're taking a safe approach, even though you're going to short them some product. The same is true to some extent with regulatory agencies. So again, if I have a product positive, do I have to notify FDA or FSIS? No, there's no regulatory rule that says you have to do that unless you're already under some kind of regulatory governance. So I would not do that, but you better make sure that you have taken corrective action, that you've disposed of that product that had the positive product in it, and sooner or later someone will come and audit your records, and they will no doubt find that you had a product positive, and they will dig into what did you do, how did you make sure that that failure to control a hazard was corrected, and how did you verify that your corrective action was truly effective. So there's a lot of things to do if you get a product positive on a lot of product, and they're all important, and you need to make sure you follow through with all of them. So if we go to the final slide. So I just want to thank everybody for attending today. I think we actually ran a little bit long. You should get an email that's going to have an evaluation. So we certainly welcome your feedback on today's content. We hope you all got some important information out of it. We do have, it looks like 5 chat questions. So before we go to those, I just wanted to announce that the August, we're going to have an August webinar. So go back to the IEH Academy and look for that. I don't know the date yet, but it will be on whole genome sequencing. And so you all have probably heard about whole genome sequencing. You may not know exactly what that means or why that could be important to you as a food producer, but it is certainly of critical importance to the food industry. So I encourage you to attend August webinar. So
well, we can take some of the questions. We've had some message to us. First question is testing recommended for products which the consumer has a process to control microbiological hazard? They gave the example of raw dough. Well, no, raw dough, I think raw dough is essentially it's a raw agricultural product. You've got flour in there. I would expect that occasionally you're going to have raw dough that has enterohemorrhagic E. coli, Aztec E. coli, salmonella, perhaps. if you're selling this to a customer who's reliably going to use that dough and with a kill step like baking, then I don't see a point in testing it. But I will tell you, for God's sake, don't sell raw dough to the consumer. Consumers eat raw dough. So we're in a situation now where raw dough, if you deliver it to a consumer, you have to treat it like a ready-to-eat food. And people in the business now selling cookie dough typically are using pasteurized flours to make sure it's pathogen-free. They're typically doing testing, and because they know that there's a bunch of consumers out there that sit down and eat that stuff raw. Go figure. Another question. Are there any white papers, references IEH could recommend for justification to not test for traditional indicator organisms, coliform Enterobacter? The only place I have seen this in writing is Jeff Kornacki published a chapter in a book where he called it out and said, you really ought not to do this. And so I think that right now nobody has really much written about it, but I think you're gonna probably begin to hear this recommendation from food microbiologists more often. I'll have to go back and see if I can remember the title and authorship of that book. It's a fairly recent book, or any of you that know Jeff Kornacki could shoot him an email and maybe he'll put it in writing somewhere else. Yes.
So I think you said it early on, but let me repeat it again. So if you get a positive for one of these indicator organisms, you as a producer, what are you going to do with that information? Are you going to treat that exactly as if it were in fact a pathogen? Because the only safe course of action to take would be to act on it as if it were in fact a pathogen. And
well, yeah, a lot of times you've dug yourself a hole. So
right.
Actually, the first thing that happens is we set specifications for these things. And I see specifications all the time. Less than 10 coliforms, less than 10 E. coli, less than 10 Enterobacteriaceae. That's essentially zero. And so if you've got that in your specifications and then you test and you find, let's say you find, 50 E. coli or coliforms or Enterobacteriaceae, now you're in a spot because between you and me, it probably doesn't mean anything. And yet you've now exceeded your specification. At that point, you've really got only two choices. Find some way to explain this and change your specification, or reject it. Bad things happen to people who have a set specification for something and then ignore it. And that can really come back to haunt you. So you either have to hold your specification sacrosanct and make sure you get it right, or you don't test for that and don't have a specification for it. Another question. When increasing sampling frequency and number of samples per lot, is the presumption they will be tested individually, or is compositing effective? You want to try and do this so that you can composite it. Most tests for pathogens have been validated for composites, like salmonella. Nearly all the methods are validated for up to 375 gram composite. So you should come up with a sampling strategy that takes maximum advantage of that. That's the way to be the most cost effective. Another question, let's see. What about when the industry requires the finished product, such as ice cream, to be less than 10 CFU per gram for ice cream? That is a very old holdover specification that was back, I think that dates back perhaps to the 1930s in some FDA literature I've seen, where they had coliform specifications on things like dairy products and ice cream. Those are very old, and they really should be rethought and something else done. That was one of the very first and most highly regulated foods, and it goes back to history with the PMO, and a lot of states have adopted that stuff too. So it's kind of problematic when you have a regulatory agency that's adopted what is essentially an ancient standard. But if anyone has any other questions, you can please feel free to email us and we'll respond to you. Gene, any final comments?
No, I mean, I agree with the ice cream. Less than 10 CFU per gram is essentially non-detect. So, as you said.
Yeah, I mean, when you find coliforms in ice cream, hey, get after your sanitation and improve it, because it's possible to have zero. But it doesn't mean that ice cream is unsafe necessarily, right, or unwholesome or anything else. So with that, I guess we'll thank everybody for their time, and hope we'll see you at the next webinar on whole genome sequencing. Thank you.
Thank you, everyone.
Thank you. Thank you.